Then we will talk about the rest people.
Okay.
Okay, okay. My camera may not be opening, ma'am. You can start.
Come here.
Yes,
Come
sir.
here.
Madam, recording started. If Deepan sir can join here, we will start the session. Madam, is Deepan sir joining? Agila ma'am, can you please help me to give that Teams link to the participants in the WhatsApp group, ma'am? This link okay? Because I have given same link. People were saying it is for that previous session. Dear participants,
Yes, ma'am.
ma'am, your your meeting details.
Ma'am, can
Yes.
you please share the meeting ID and password in the WhatsApp group, ma'am? People are struggling.
Yes, I'm doing it.
Meeting
Ma'am,
ID
what
and
you are-
password alone instead of link.
Okay, only ID they need. Okay, I'm
ID
sharing.
and password. Quick, ma'am.
The one which you have already pasted, shall we remove?
Yes, ma'am. You remove that and you can send them again.
Yeah.
I think it is connecting them to the earlier one.
Yes, sir. Yes, madam. Yes, now I think it is working good.
Yeah. Yes.
For everybody.
Yeah,
I'm
people are
sharing the
joining
link.
now. Yes, ma'am.
Yeah, I'm admitting everybody. Still, some people are going to that one.
Yeah, please check whether Deepan is joining. And you also make me as a presentee, ma'am.
I'm correct. ఎందుకమ్మా
నేనున్నా ఇక్కడ సాస్ కావాలంటే చెల్లి
ఇంకేనా ఒక వచ్చింది
అన్నీ ఉన్నాయి నేను నాలుగు ఉన్నాయి ఇవి ఇయ్యి
Ma'am, kindly mute the participants, ma'am.
దాని మీద ఏవా
Oh God.
Anita, ma'am.
Yeah, I'm making them to mute now. I'm doing multitasking.
Deepan have joined. Kindly make him as organizer.
Yes. I'm checking. Deepan sir, kindly raise your hand as I am allowing everybody. Thank you. Thank you, sir.
Yes, ma'am. Let's start, ma'am. Very good
Yeah.
evening, participants. Very sorry for this delay because of this technical glitch. It was happened, and I know you understood the things. And very warm welcome to all of you for the day 3 of our 6-day online FDP on demystifying transformers, the brains behind generative AI. On behalf of all the participants, it gives me a great pleasure to welcome our esteemed resource person, Mr. Deepan Raj. Deepan Raj is currently working as a technical manager in the data science division at HCL Tech Private Limited. His areas of expertise includes generative AI and computer vision. He completed his Masters of Engineering in VLSI Design and Embedded Systems from prestigious Madras Institute of Technology, Anna University Campus, Chennai. And the present he is pursuing his PhD in the field of artificial intelligence at the same institution. He has also been honored with the Indian Book of Records for teaching artificial intelligence to 800 students in a single day. With his rich academic and industry experience, Mr. Deepan Raj has trained faculty members and students from various reputed institutions, including several IITs and NITs, through FDPs and workshops on the domains, namely AI, GenAI, and robotics. We are truly privileged to have him with us today, and I'm confident that His session will be highly insightful and inspiring for all of us. Let us all extend a warm virtual welcome to Deepan Raj, and we are honored to hear his talk on transformers and its variants for the first session, followed by advanced GenAI tools, namely LangChain, RAG, etc., with an hands-on. Over to you, Deepan. Thank you for being with us.
Thank you. I'll start with the presentation. Hope my voice is clear, ma'am.
Yes, yes, Pa.
Okay, I'll just share my
Sir,
screen.
your voice is clear,
Yes, ma'am. Okay.
but can you turn on your camera?
Ma'am, kindly mute the participants.
Okay. Yes. So, good evening, everyone. So, we'll just deep dive into the transformer section right away. So, let's try to understand the concepts behind it, and I guess the time is of the essence. I'll just skip to the important section so that we get things accommodated right away. So, the most important part of any neural network, and I'll just skip this slide. Basically, whenever we wanted to train a neural network or any sort of models, the data has to be converted into numbers. That's the most important aspect of any model training. So in that,
online. ಇದು ಆನ್ಲೈನ್ ಕ್ಲಾಸ್ ಇತ್ರಿ ಒಂದ ಅಟೆಂಡ್ ಆಗ್ತಿದೆ.
Ma'am,
okay. Yeah. So basically, like in order to convert every data into numbers, it takes quite a bit of a challenge when it comes to natural language processing, because like all these words are basically ASCII representation, in terms of character level, but we cannot just certainly push every character into neural network, right? So for example, if I take a neural network and if I don't do this embedding, like imagine like I have 10,000 neurons that accept 10,000 characters, because every word have few characters, and that will create a lot of complexity, which means that character embedding is a very tough challenge, because we cannot basically do that, because if you see the two words live and evil, basically the same, but still the characters are kind of so the characters are the same, but the word is totally different, right? That's kind of a problem which we see here, which means that when it comes to character level embedding, we can't deny the fact that the model can gain any insight from that, which means that we have to move to a concept called word embeddings, where we will convert every word into numbers. And that's the most feasible way of doing things, because yes, for every word, we can give some unique tokens. But now the problem is, every time I get a new word, I can just come up with a number and it will be done with it. But imagine I get a lot of new words, let's say father, girl, son, boy, mother. There are like millions and millions of words which are available in our dictionary, and we can't certainly just number it. For example, if I basically take let's say if I number this girl as 001 and number this maybe boy as 010, both you can see it's like not much different. And if I take this word daughter and if I number it as 100, let's say a girl can be a doctor, correct? Which means that obviously like these two numbers should be little close enough so that the model can identify there is not much of a big difference in that case. That's one thing which we have to keep in mind. Which means that how do we solve this problem? Making sure all the numbers are very similar to each other. Let's say the girl should have a number like 0.01, the daughter should have a value as 0.03 or something like that. So the difference between this magnitude should be little close enough so that the model can find it little easier to understand this nuances. And yes, in order to do that, we have to create some concept called word embedding. To simply put, we just create a certain set of certain set of columns of information, and we try to create that in terms of multi-dimensional space. Basically, we won't be doing this. We'll be using a model output to do this. Basically, like all the words that has some meaning one way or another and some other dimension, it will be close to each other. For example, if I take this word girl, the girl and the word daughter will be close to each other at one dimension. At maybe at dimension one, it will be close to each other. And the word woman and girl can be close together at dimension number three. Likewise, if I can able to represent all these numbers on a 64-bit dimensional space, no matter like what the word it is, if there is a meaning or if there is some a tangible meaning between these two words, we can able to get that particular information very easily. So that's called word embeddings basically. And yes, word embeddings became very popular and becomes a popular choice for training a model. And yes, you can just create given this tokens, and then convert those tokens into word embeddings so that this word embeddings will act as a pillar for converting your words with the rightful numbers. So once the numbers are correctly done, we can just train any model with that. But again, we know that feed-forward network cannot do that because it lacks, it cannot handle sequential data. It just considers the present data, and there is no memory or past data involved. So that means we can't rely feed-forward network for sequential data. So what are sequential data? Yes, NLP is a sequential data, sound, weather forecasting, all comes in the category of sequential data. So people relied on RNN, LSTMs, and transformers, and we know that even RNN and LSTMs were struggling a lot to do this because if I take the RNN architecture, it is basically sequential in nature. Yes, it can handle multiple data at a given time, but the biggest bottleneck is every time it unrolls to a different time step to get the data. In order to process this X of t, we have to process all these data, which means that we have a sequential bottleneck. And to understand this data in a much more better fashion, we can't even do that. Basically, like, yes, with RNN, we can do many stuff. Basically, the concept derived, quite earlier before transformers, and it was a decent method to basically go with it. But basically, yes, RNN lacks in many areas. If I show you this formula, it just takes the previous old state into consideration and tries to, add the current data also together. So which means that whenever the model tries to take a decision, it won't consider the current data, it will also consider the previous data. But now the problem is, when it comes to, this is the expanded version of it. So basically, we have the previous state data and the current state data, and the weight factors will be associated towards it. And you'll get the next data which will be prepared. For example, if I take this h of 1, this basically reverses on the previous data and the current data, you get h of 1. And if you want to go to x of 2, you should have this h of 1 and x of 2 to get this h of 2. Likewise, for every data, you should add the previous data, which means that for not to get this x of 3, I need to process all these informations together to get to this h of 2. Now, what does h of 2 contain? This h of 2 contains information of x of 1 and x of 2 together. Right? So we don't have a separate ideology to make sure like which word is important, which word is not, because everything is kind of additive in nature, and that's how the model has to bring it up. So which means that how do we solve this particular problem in hand? So basically, let's say yes, we can able to create the outputs and other things, but the problem is like it is a sequential model, and it cannot, it cannot like understand a lot of nuances. Let's say basically it has a problem called exposing and vanishing gradient because like it is additive in nature, right? So I show this data, right? So every time if I take this to this formula, you see, right? So it is always adding things together. So it adds up information every time it goes, which means that like this h of 1 will be added with x of 2. At some point, h of 2 will be bigger than h of 1. So that's how it is seemed to be like working out. Which means that it's going to be a problem because the current data will create a huge ruckus. The current data will create a huge ruckus because at some point of time, if this x of 3 is important and h of 2 creates a very large number, even though, let's say, for example, if I take this h of 2 to be 100 and x of 3 to be, to be 10, like even though I multiplied by like, zero point 0.1, I end up having it as 10. And if I multiply this as 0.1 as a weight value, still this is a huge number and that will manipulate the data. So that's a bit of a pickle in this point, and that's why RNN cannot handle a sequential data in a very lengthy sequence, basically. And when it takes the back propagation, it is basically back propagation through time. It goes chunk by chunk, section by section, and back propagate on data. Because it has to do in this fashion so that all these words which you see is kind of accommodated in this particular area. So because every word has its own importance, so based on that, we'll calculate the weight, and one single weight will be updated at some point of time. And yes, there's another more factor called vanishing gradient, where this vanishing gradient is another huge factor, because exploding gradient somehow can be solved with tanh, because the tanh activation function has a value between minus and +1. It can be able to give you some different, altogether different or a lesser gradient value. If you see this particular example, here the gradients are exploding without tanh, and if you have this tanh, the gradients are not exploding, it is like maintaining to a certain point. But as I told you, like if I show you this example, there are a lot of important words here. And imagine this is my final word which I'm trying to process with RNN. What happens? It tries to take in all these words as h of t minus 1. Correct? This would become h of t minus 1, which means like all these words will be appended against each other, and it will lose the importance of which word is important, which word is not. And sometimes it might be like positively reinforced, and sometimes it can be negatively reinforced, and meaning that the last few data will not be much more useful because of the overwhelming previous information which is being put down there. Basically, it will forget over the period of time. And yes, there are a lot of factors which can be cultivated. We had LSTM, we had GRU. These are basically like are much better in handling the data in terms of memory. It can able to do to a certain length, but still, it is even difficult for the model to handle a very long text. Let's say 1,000 words or beyond that, and it is still sequential, and it takes time to take. Yes. Yeah. So basically, like, what is sequential? Because like in order to get x of 5, I need to have this h of 4. In order to get this h of 4, I need to have this x of 4 and h of 3. Likewise, in order to process this x of 5, I have to take from h of 1 and x of 1 and process all the way up to x of 4 and h of 5, right? So to get this, I have to follow this process. Even though I have a powerful GPU with me, I can't accept the fact I have to go sequentially. So this is the two important columns, and most importantly, context. Context is a very important key factor. So if I give you some examples on it, let me just show you one example. If I convert every word into embedding, because that's where the model understands. Let's see if I take you towards this example. AJ stock is a QT. Let's say AJ okay, just write it here. AJ's dog is QT, and let's say AJ looks like a dog. Okay. If you take these two words, if you take these two particular words, even though the words are the same, but when you see this particular two sentences, the context changes entirely, which means that I cannot rely onto a simple word embeddings, correct? Because word embeddings will just create this into a multidimensional vector value, and this word will have the same embeddings for sure. So, and because of this, it creates a problem for the model to understand its nuances. Basically, uh, the model will understand that these two words are the same, but still the context differs and the model failed to recognize this. Which means that like understanding the context between these two sentences is not that easy for a simple network, right? So that's where people decided, okay, so we need to have a powerful network, and that's where transformers came into play. Okay, so transformers, as the name implies, it has a concept called attention mechanism. That's what the paper reveals. It is attention is all you need. So what they basically do is they just created a simple architecture that has an encoder and a decoder in it. So basically, like if you see this particular architecture, it is basically created for doing this translation task rather than a simple classification or generation. They were focused on creating a model that can translate things in a much more better way. That's why the encoder and decoder were created. And we can see that it's a very simple architecture. You see, like, we have very less networks to the layers of neurons that is there, basically. Give me a second. So, yeah, so basically, this particular architecture as an encoder and the decoder mechanism. And if you see the architecture, it has this multi-head attention. That's the most important part of the transformer. Let's try to understand like what really happens within it. So if you take a regular RNN encoder, we always convert every word into one single pass and you get some memory. But in transformers, you can do that in parallel. Basically, like all the words can be given at one shot, and that is a huge leap forward because you don't have to process things in a sequential pattern like how RNN does, which means that you can do everything at one shot and you don't even require any sequentiality. You can process all the data in parallel. And yes, if you see this particular word which I just told you, like this dog is a cute and AJ looks like a dog, even though I convert this word dog into an embedding, both the word will have the same embedding, but still the context is entirely different. So how do I change this particular context, or how do I include this contextual information to these sentences? And that's where people realize in this particular paper, what if we add the position? What if we create the positional argument alongside the embeddings? Such that it becomes even more better in terms of identifying this content. Let's say dog at position number 2 as a different embedding, dog at position number 5 as a different embedding, which means that like both the dogs can have the same word, but still it's a different position, which means that it should have a different embedding. So with this additional positional embedding, people are able to create a very good contextual information on all the words rather than just blindly believing that all the words or every word in every different sentence will become the same. It's not the case because every word will behave differently at different sentences based on the particular context. So which means that if I can able to capture that essence somehow with positional embedding, yes, that would solve a lot of problems. That's what Transformer did, and they use a simple positional argument, basically a simple formula to get this positional information. So if you see this formula, you have this I 2i divided by the D model because every word embeddings will have a 64-bit dimension, which means that like you have to calculate you have to convert every bit of information into this particular value, and this position will be this one, like 2, 3, 4, 5, and this will be calculated for even numbers, and this will be done for odd numbers. So that when I see this output, it looks something like the sinusoidal waveform, and that captures not just the word embeddings but also the position information for the entire embedding. So that's what happens. So which means that all I have to do is I just have to add my embeddings of dog with my positional encoding. So if I can do that, basically, you know, uh, we can basically convert uh, every bit of word with more context information. So if the context is clear, then it is even more easier for the model to understand the information sent. So that's what transformer does. So basically, we take the input, we convert into input embeddings, and we also take the positional embeddings, add these two informations together, and that will be further pushed into multi-head attention. So if you take multi-head attention, like what does it do? So basically, like this particular attention mechanism comes with the concept of self-attention. So what is self-attention? So if you take this particular data, if you see, like, the sentence is this particular sentence, the big red dog, and what we do is we're gonna place these keys that faces to the same sentence again. Let's say the first word as a key facing towards the same sentence, the big red dog. The second word as a key that faces the same sentence, the big red dog. Likewise, I'm just gonna place all the words in the sentence to the same sentence again. So after that, I just create this attention vector altogether. So how this attention vectors are created? Basically, how much focus this particular word can be given to the sentence. If you take this particular sentence in hand, the word B will be given more attention because it's the self or the same word will definitely have most of its attention for the given word B. Okay, so if you see here, like the entire diagonal portions are in this particular way, right? So it is basically will be higher than the other words in the sentence. But what's most important is if you see the next important word, you see like the numbers points to the word dog, right? So for the first word D, even though self-attention focus on the same word, the next important word is focusing towards the word dog. Similarly, for the big word, it is focusing towards the word dog, and for the word red word, it also focuses to this dog, which means the next important word places the model to attain information as yes, this would be the next important word which I have to focus on in the given sentence. So with that, we'll be creating this attention vector altogether in this particular section. So with this attention vector, we were able to create wonderful numerical representation of all the words in the given sentence, and that can give us a better understanding. Now, how does attention mechanism work in the first place? Is if you take this particular section, let's forget about this. Let's take the simplest of the formula. This is the formula behind it. So we have three things. One is Q, K, and P. So Q stands for query. Okay. K stands for key, and V stands for value. Okay. So that's the explanation of these three terminals called Q, K, and V. Now, how these are helping the model to find the attention behind it. So if you see the formula, it is Q into K of T to the dot product of V. So and you also divide it by the dimension of the vector value so that you have the same dimension space without any scaling factors, avoiding the scale of different words. So you just divide it so that everything of the same scale, you just multiply it. So basically Q are basically your query vector, K are the key values. If I go back to the previous slide, this would act as a queue. This would act as a queue, and every of such individual components will act as key. Will act as a key value. First thing, like you just multiply this into this. Basically, this is a vector, and this is also a vector. You just multiply these two vectors together, and what you do is you get you basically get a dot product output of these two words, and you do a softmax classification on that. So if you see here, Q and K is multiplied, you demonstrate it, you scale it out, and then you do a softmax activation function so that this Q and K, when multiplied, it shows which words are important and which words are not, on terms of a value. So which means that at some point in time, this would have values like 0.7, 0.01, 0.02, and 0.27, something like that. Which means that this kind of confidence value will be, probability value will be created by the attention vector, sorry, by the softmax attention function. And with that, we multiply the raw value. The raw value stands with the entire data. The value will have this, the big red dot together. And that value will be multiplied against this softmax, and you arrive to this particular value, something like this. That's how attention mechanism works. And if you see, like every vector components will have a linear layer that has the weight values, and this weight value will be adopted to make sure that dot products are in its own alignment. Because we cannot just simply just multiply V, K, and Q, because that won't make sense, because it's just words. We have to convert those into a weight and a learnable factor so that these values will change its weight, making sure all are accommodated correctly. Because maybe initially it might focus on the word dog, and it might have a huge focus on the word the. But when it back propagates, it knows that the word the and the should not focus much. It should focus more on the word dog as an important word. And very similarly, like, you have other words, the big red dog, and you kind of get these information from this weight value. So the weight value will adapt during the back propagation or during the learnability, and it gives you some important notions behind it. And if you see this, you can see there are multiple heads behind it, right? It's not just a single attention mechanism; it's a multi-head attention block. So what does multi-head attention block does? So basically, this multi-head attention block is basically you you kind of give the same section to multiple heads, and every head will give you a different output. You just average it, you kind of concatenate and average it and give it to the next layer. So basically, it's like, 3 to 5 persons doing the same operations again and again and trying to get some, outputs and to average it up. It is very similar to the ensembling concept, right? So where we try to average the contents altogether to get an information. So very similarly, that's what we do in the multi-attention block. So the multi-attention, we'll have multiple heads. And again, more the heads, more the complexity, more the learnability. But again, it will take a huge computations for sure, and that has to be taken care of. And most importantly, like once the multi is done, we just do a normalization, and we also have a skip connection here. If you see here, we have a residual skip connection so that we are not taking too much information about the multi-attention output alone. We just add the previous information before it goes to. Let's say basically the embeddings of every word will be added against each other. So this helps the model in check so that the identities are preserved. It is not channeled too much towards the attention block. That's where this addition and the normalization is being done. So once it is added, you normalize it because obviously it is overfitting, because you see that there's a huge numbers for the self attention values. So you have to reduce these values. In order to do that, we do a normalization and then push it to a feed-forward network that basically grinds in all these informations together. Because like every data is like kind of separated right now, because every word has its embeddings and every embedding gets some vector values. And now all these vector values have to be grinded somehow. And once it is grinded, you get some meaningful information. And once that is done, you can see, right? So if I show you the bigger picture, the output of the encoder goes to the decoder, right? So which means that here also the activity is the same. So you get the output. Basically, like this, as I told you, this is a translation problem, right? So let's say we take this English to French translation. So like let's say if you have 4 words as an output, as an input, you might have 4 to 5 words as an output. So those output words will be given here. Again, same embeddings is done and the portion encoding is done, and then you push it to a multi-attention. But here, if I go back, the output is given here. Before the output is processed, you again follow the same process and you do a multi-head attention before you go to the encoder decoder attention. But if you take this multi-head attention, it's not just a regular multi-head attention, it is a masked multi-head attention. Why it is a masked multi-head attention? Because this is the output. If the model sees the output as it is, it will easily overfit, it won't learn at all. Because it knows the output, it can map it very easily. in order to avoid model, being prone towards, knowing the actual output, we mask the information. Usually, we just mask information section by section, by pass by pass, so that the model doesn't put too much strain in just bypassing the learnability. So that's where the mask, multi-attention happens. So every word will be masked to every other word, and slowly, we'll unmask these contents. So once that is done, the output of the decoder the input of the decoder and the output of the encoder will be combined together to form this encoder-decoder attention mechanism. Now, in this encoder-decoder, the value Q will be taken from here because the query is, sorry, not this one. Let's say this is your encoder output. Let's say this is your encoder output. This would be your Q value. Okay, this will be your Q value, and this individual comment can be treated as K and also V. Okay, so both the entire word will be considered as V. Individual components will be considered as considered as K. So which means that this word and this word will be multiplied first. You do a multiplication, do a software classification, and then you multiply that to this particular word entirely. Likewise, you do this on and on and on so that you can map the encoder output with the decoder output together. That's where the model understands, okay, this word and this word connects together, and this might be important. Likewise, slowly the model gains its understanding on connecting these words together. Let's say for this word English, the big red dog, the output should be Lake Ross Chain Dog, and it is well learned doing this encoder decoder attention form. And again, once that is done, you again going to add this information as a skip connection, just like a regular network does. And then you do a feed forward, you mix things up together, and finally you have a linear layer that will make sure the output which you're looking for is as expected. Because sometimes the output, can be different set of. It can be many output, it can be one output. So based on the requirement of your application, the linear layer will make sure that desired output values or the length are met. So simply put, you have the word that goes into this encoder and you have the output that is also going into this encoder. Both will do this position encodings and add things together, and both happens to enter into the multi-attention block. The only thing is that the decoder will have a masked multi-attention, and it does give some attention outputs, and those vectors will be given to the feedforward network, and the output is given here as a multi-head cross multi-attention where encoder decoder will combine together and knows like which one is which, and finally you get some output, something like this. And this is how the transformers are built. I'm just kind of rushing it through, but I'm just stopping it here just to make sure, do we have any doubts or clarifications before I move on to the next part?
Dear participants, if you have any doubts, you can ask sir now. If any of you have doubts, kindly raise your hand.
All right. So, to summarize the facts, basically, encoder and decoder relies too much on the attention mechanism. And if I show you this attention mechanism, it's a very simple ideology. You just multiply Q and K. Q and K can be the same for encoder, but for decoder, the Q will be from the encoder, K and V from the decoder block. That's how the mapping and things will happen. And this linear layer will have these weight values that decides what type of V, K, Q will be multiplied. Okay, this is where the learnability happens. Okay, without this, the model can't learn anything because not every time the model can get the right attention outputs, right? So slowly when that propagates, it updates these weights to get the right things to be done. Okay, but with this, the model gains superiority, and both this encoder and decoder became very, very successful in terms of understanding what is language and how to map words to a different thing. Basically, the encoder part became very strong at understanding the context of the language, what is the context and what is English, and the decoder block became very, very much flexible enough to map English words to the French words, which means that this became more of a causal relationship, and this guy became more of contextual relationship, understanding more about the given data rather focusing on what to be generated or something like that. And people realize the potential of this transformers And the only thing which they can do with the transformer is just translation, because it has a encoder and a decoder combined together, which means that you cannot just simply just give one input and get some output with transformers. You can just do a translation in a much more feasible way. But what about other methods? What about generations? How do we get for a query in our chat GPT or any different LLMs? How do we get these outputs? Right. So that's where people realize, okay, so since encoder and the decoder are really good at understanding English, why can't we split this? Why can't we split these two architecture as two different architecture, making sure both will work indigenously against each other. So basically, what happens here is you kind of take the encoder block and you attach multiple encoder blocks together to form an architecture called BERT, and you have a decoder block called GPT. That's where your chat GPT and other different decoder architectures came into play. Basically, like it is a multiple decoder block that has been combined together. Because if you combine multiple blocks together, the reasoning will become quite better in terms of understanding the nuances between the words. So that's why BERT and GPT became very famous, especially GPT became very much famous. I'll just come to the point. But basically, yes, BERT it's a really good model. It can do a lot of a lot of handling. Basically, like it is much suited for classification and for Q&A. Let's say if you have a context and you ask a question, to answer from it, it can easily do that because it has a concept called mass language prediction. This is how the pre-training happens basically. It has an MLM and it does this NFP. So basically, MLM is something like you have a sentence, you mask few words, let's say one or two words, and then push it to the BERT model, and the BERT model will try to find these two words. That's how the pre-training happens, and also it understands whether sentence B follows sentence. If you have two sentences in it, it's a classifier task basically. It says like whether sentence B follows sentence A or not. So with these two goals, pre-training happened, and it was basically consisted with 12 layers of encoder blocks, which is basically 12 of such encoder blocks have been given, and the large version of BERT has 24 layers. And you can see the parameters. It is just 110 parameters, and these are 340 parameters. So these are not typically language models. This can be very useful in terms of this can help in terms of for classification and for question and answer. It can't certainly generate contents. Okay, it might not really good at generating content because the architecture is put in that way because it is too keen on understand the context of the words rather generating or reasoning on top of that. And if you see, like there are many different variants developed, for BERT. We had Roberta, different varieties, I would say. And you can see like they use different methods, like instead of using, they kind of skip between this NFP because that was creating too much noise, and they started creating more data and train it for longer duration. And they also use this byte level BPE tokenizer. So basically, like we talked about embeddings, right? So there were a lot of other methods of embeddings, like basically Elmo, byte level BP, word piece tokenizer. There are different tokenizers that work even more better than basic embeddings because sometimes we make a lot of typos and other things, right? How these typos are understood by the model, how a new word is handled. Because I don't have a word which is very new in terms of my corpus. How do I find those new words? How do I align those new words in my embedding space? So those things can be well handled by this byte level BP tokenizer, and it is proven to be proven to be much more successful in terms of a better model rather than the normal OG BERT. And yes, we also had this. Yeah, this is the byte level encoding basically, byte pair encoding and byte level BP. So byte pair encoding is something like you kind of create different tokens so that you can merge it whenever required, which means that it can reduce the number of tokens altogether. And not just that, it will convert all those common pairs into bytes so that multilingual and programming, emojis, Unicode, let's say foreign script or anything, can be treated as one single into a one single embedding space, converting everything into a byte value. But if you don't do this, every Unicode will have a different representation, emoji will have different representation, code will have different representation. Because of this, the generative or understanding capability will become much more lesser. And not just that, we had Albert. There are many different models which was created, becoming better and better. And they were focusing more towards a small model called Distilbert, where they kind of reduce the model size to 6 layers. It's like kind of a teacher-student architecture, where you try to make the model smaller by pre-training with a teacher model, so that it becomes 60% faster and 40% smaller, and basically retains 90%, 97% of the bird base. So that's where deployment became very feasible, and we had mobile bird, tiny, but there are many different birds which are created. Okay, these are different variants, and also we had the ZBERTA, where this instead of having this positional embedding, they went to this disentangled embedding. Basically, like you have a relative position embedding, so that you don't focus more towards position, because sometimes position can also be irrelevant, right? So to have that in hand, we have this native position embedding that made sure it understands the word into much more better context. And yes, these are some variants which you saw. And then comes the GPT. GPT is a decode-level transformer, and it's a causal self-attention. And yeah, the most important thing is bird can read information from left to right and right to left. It has a more detailed understanding of the context. But this GPT can only see a token from the left. That is only just from left to right. It can only see the past data. It cannot see the future, which means that it is much better in terms of generating contents, rather doing some classification and other stuff. It can generate in a much more better way. That's why this auto-regressive concept came to it. It is basically focused towards next token prediction, and you have this tends to have basically towards a few short form, because in 2018 when this was published, it was doing a very decent job, but still it can't able to generate things in a much more better way, because it was just trained onto some 7K unpublished. But when GPT-2 hit the market, they upped the size to 1.5 billion parameters. If you see, the first model has this 117 parameters, and slowly they've created many different variants, and the biggest of the variant of GPT-2 is 1.5 billion parameters. And they have trained onto a very huge web text data that has been taken from Reddit links and different news forums and other customers have been pushed, and you can see the vocabulary size is also being improved to 50K vocabulary, and slowly it attains the capability of zero shot and few shot prompting, where you can give few questions and you can ask them answers. It can easily give you answer very easily. You can summarize, you can translate. It was a much better replacement than BERT and GPT-1, but still the context was small, and that's where GPT-3 came into play. And you see that from 1.5 billion in 2019, in just a year, they created a flagship model that has a size of 175 billion parameters. So if I just say 1 billion parameter requires at least like 2 to 3 GB of GPU to load, and imagine like how much space it will take for the model to be loaded with this massive amount of parameters, right? And also they had a smaller model of 13B variant, that's called mini variant. And yes, it has 96 layers, which means like basically it has 96 of the decoder blocks of different changes, and there's 96 heads. And the context window is also becoming better. And they had a 300 billion token, which means that they use this common crawl method, basically like this, what is that? Web scraping method to scrap almost all the contents available in the internet. And they were able to get things done in a much more better way, and that became much better in terms of understand the context. And basically it can give you answers with just one prompt, or give few examples, and the model adapts without even updating its weights. But still, there was a threat of having a token limit because it can only attain 2048 of tokens, which is pretty decent enough for a decent sized data. But if I just give some 2 to 3 research papers together and ask you to summarize, it won't work because it has a limited context. That's why GPT-3 was really good in terms of answering things, but it was not handling huge data or giving huge outputs together. And that's where GPT-4 came into play, and it became even more popular because of the size, because it has reached around 500 billion parameters, and it has a token length exceeding lakhs, of tokens, which means that you can easily load multiple documents together at one single shot and expect it to answer it very clearly. So that's how GPT evolved over the period of time. But the predecessor transformer paved this way, right? So without transformer, the decoder structure wouldn't have been explored this way, and also the embeddings, inclusion of this portion embeddings, created a pivotal, method to create better context. Yes, even though this byte level BP and everything comes and goes, portion encoding created and made better contextual information for every given word. And just because of that, the model became much powerful in understanding contents on a real-time mode. And that's how you see there are a lot of models which is available in the market, and it can able to give better results. So do we have any doubts or clarification? I hope it's fine if I just borrow some 5 to 10 minutes so that we can see the hands-on part as well, so that we can circulate and understand it even more better. So I have a simple implementation for transformer architecture. If you see this particular section, just note this down. All you have to do is just go to the Colab and just go to the GitHub tab, search for the handle name Deepan Raj M, and go for the repository GL. Okay, go for the repository name GL, and if you scroll down, you should see this particular program called transformers.ipynd. It's a replica of the original transformer paper which I've just created. Just open this right away. Yes, so basically what I did, I just created the transformer architecture altogether. So I just created a transformer architecture altogether where it has the portion encodings, the encoder, decoder, everything combined together, and it starts to do translation. Okay, so let's say like I have two versions of it. Basically, if I show you that, yeah, so I have like two versions of it. One is like using model from scratch with big data set, and this is the smallest of such, like using just two, three, some 5 to 10 sentences inside, and creating the French sentences. We can also train a model that can do a transition with a small data set. Okay, I'll just teach you towards it. First, let's try to run this code because it has to install these components. For the ones to start with, I'll just pause for a minute so that you can note down this program name and we can get started. So go for this program, go for this handle, go for this repository.
Deepan, we could not hear you.
Yeah, I was pausing for a minute for like people
Okay,
to
okay, fine.
just check on this program. So yeah, so hope everyone has opened this program, and I kind of created a few other things like scoring methods also, because it's also essential to evaluate contents. It's also part of the data. So what I did is like I'm just downloading the transformer tokenizer alone, because we have to convert this into tokenizer and embedding. That one is required. So I'm just using this Helsinki NLP Opus MP in French, because it has both the languages embedded together. So we had English and French languages together. So the converted embeddings will have embeddings for both these languages. Because if you use an English embeddings alone, you will get error for this Unicode, because French basically has a different ASCII and a Unicode representation, which you have to avoid. So what we do here is I just load this tokenizer in the model with me so that I start to generate. So in this case, I'm just using a predefined transformer model that does this encoder decoder together. This is the model name, which is taken from the Hugging Face section. So where I'm going to load this model and I'm going to do the translation to see like how the translation works. If I show you the output, so this is the scoring method. So in this case, you see the input. All the inputs have been given here, right? So hello, how are you? I'm fine. What is your name? And all these words are there. And for the different sentence, we have different outputs for the same words. So if you see the scoring mechanism, this is the reference and this is the predicted words. You see like bonjour, both are the same, but the problem is it has a dot here that change the entire output. So which means that we need to do some pre-processing altogether to make sure we get the right values. But if I take the Rouge one alone into consideration, it gives me decent enough output. Only few things are totally different. And again, sometimes we can't possibly say that this is entirely wrong, because Duo Primacy is also correct, but it has a different pronunciation towards it. And since it's the n-gram based evaluation approach, the numbers are fine. Numbers are like this. But anyways, all I did here is I just loaded the model, toggled towards the sentence, enumerated towards each and every sentence, converted those input data into tokenizer, and that tokenizer data is given to the model to generate the transient output. And with that transient output, I just get the actual prediction words from the target tokenizer, and finally get the reference from my input data set and the prediction together, and just calculate the blue and Rouge score. So with the blue and Rouge score, I just give you this output. That's what you are seeing it right now. Okay. Now, if I want to train a model from scratch, instead of me using a pre-trained model which is looking something like this, because this kind of creates me some output. Yes, from the prediction, I can just, as you can see, like these are the predicted content from my model. This is a pre-trained model. Now, what if I have to train my own model for the same? So that's where we are going to build our own model. So for that, we require tokenizer and patch sequences and basically TensorFlow, which is what we are going to use for creating our own model. And if you see that, I'm going to use the same English sentence and the French sentence. And first thing is like I'm just going to convert every token into numbers, every word into tokens. And I also mentioned this overview vector. I'm not using this byte PP or any other fancy method. I'm just going with a very standard approach of converting every word into numbers. So you see that I just load all the data, all the sentences, see for the unique values, and convert into tokens. And for the same, I'm going to do for the same for both English and French sentences, and make sure like what's the size of my vocabulary and just keep it in mind. Now, here's where we're going to create our own transformer block. In the init block, we're going to have the encoder embedding, decoder embedding, positional encoder input, and the positional encoder target. That's for encoder decoder positional embeddings. We will have an encoding layer, a decoder layer, a dense layer that's going to be like fitted at every different places. And if you see it in the encoding layer, we'll have the multi-attention. Decoder will also have a multi-attention. We're just going to combine this together and make it. And positional embedding. So this is the formula which I showed you, right? So the same formula is applied here, and you just certainly do it. And you see, right? So basically it starts from 0 and hops to a step of 2, which means that like only even numbers will be taken for this angle rats of sine with sine formula. For cosine, it starts from 1 and goes at 2, which means that it goes at the odd value. So angle rats for both odd and even combined together, you get the actual position input. Now, in the call function, what I'm going to do is I'm going to call the encoder embedding, which is from my input data. I'm going to convert my input data into encoder embeddings and then add this position embedding together. Okay. Now, this ENC contains both the embeddings and the position embeddings added together. Similarly, same goes for the decoder part also. Now, The encoder part is going to accommodate this encoding layer, which you have just initialized here. That's going to accept. The encoder input. Similarly, you can see that. So this is my Q and this is my K. Because K and V are the same, so we will just define it that way. But in the decoder part, you see, right? The Q is from the decoder, and the output of my encoder is going to be my K and V. Sorry, this is going to be my K and V, and this is going to be my Q. Okay, and you can see like this is the K and V, and this is my Q. So that's the change which you're going to do here. And finally, you're going to push it to a dense layer, and we have been done with it. Okay, and yes, once this is kind of initialized, and you would see that the decoder will not have this masked thing alone because which I haven't implemented. But this is a very simplest of implementation, because if I just start adding few more attention mechanisms, it will become even more bigger in size, and I cannot train it in Colab. So that's why I just limited this thing to encoded decoder output, just like that. Okay, I just combine it. I compile the model with all the relevant information. Like the dense layer is going to have 64 hidden layers. 64 dimensional space for all my embedding size. That's a vocabulary size. And TFF is going to have 120 hidden layers. That's the feedforward layer. And yeah, number of it is going to be 4. And everything is compiled, and we just start to train the model. And once it's trained, I'm just going to do the same operation which we did above, right? So like in the previous example, we used a pre-trained model and we started loading it, right? That's what I'm going to do here. So I'm going to convert all my input words into my output words, and finally I just evaluate it and get some results. If I run it, it might take some time to train on, because it is again, the architecture is slightly huge and it might consume my GPU very exhaustively. But yeah, so if you see it, so the training got started, and if I train for more and more epochs with more and more data sets, the model become much more better. But if you see here, it's a ruse, because it is a very small data, and the model is not picking up anything at all. Everything is becoming OV, and everything becomes zero. But when I train the model for few epochs with a bigger data set, and if I show you the output, okay, yeah, this has been trained for only one epoch, but you can see like it is trained for only 20 epochs, and the model was not giving certainly the rightful answer. That's basically sorry, wait a minute. Okay, I guess I have to run this one. This is not the one. If I run this one, you could see the results populated correctly. But yeah, so you can just give this a try. It will take some time to train, because I'm going to train with 10,000 data together, and it will take some time. But this is the entire implementation. If you wanted to add this mask encodings, you can also do that. Okay, just that's how it is. Okay. Let's hope this is well and clear. So if you have any doubts or clarification, we can discuss now.
Deepan sir, actually one person has requested some question in the chat box. Silvam E has Dr. Silvam E has asked how the attention coefficients calculated in masked multi-head.
Yes. So basically, if we see here, yeah. So if we see this particular word, right? So all these initial words, if I just place it down here, what happens here is the first word which enters here will only have the first word. Remaining thing will be masked. We'll have nothing here, which means that like only focus will be given only for the first word. That's all. Because if I have the entire output, the model knows like what the output is, and it can easily relay information together. So doing the masked validation, the query will be this, and the key will be there, but all these 3 words will be masked. That's how the masking is. So if you see the output here, you see the first word, everything focused towards the same word, because it's only one word being enclosed, and the next word, when it comes, the second word will be unmasked, because that's the second input which we have. Likewise, for every new word coming inside, we unmask it one by one, so that equal attention is given for every other word. That is very essential, because the output should not be revealed right away. The model might find it very easy to break things up. That's how the calculation is done. and if we take the QKV, Q will be from my encoder, and V will be taken from my decoder. That's how it is.
Okay, sir. He is again asking, will the same approach work in GNN?
Okay, what is CNN? I'm not sure.
Sir, what do you mean by GNN, Selvam, sir? Graph Neural Network.
Okay. Okay, I have very less idea on that, but it should possibly work because it's an attention mechanism. If you can able to sequentialize content in a in a sequential fashion, then yes, it is doable. That's how
Possible.
it is.
Mhm.
Yes, it is possible for a even, but we have to make sure the data are placed in a sequential fashion so that it can learn it in that accordance.
Okay, sir. He conveyed. Thank you.
For some reason, I cannot see the text over here.
Sir, he is unable to uh, audible. His mic was not working properly, so he said like that. And one more person from our audience, Angelina, ma'am, kindly
Yeah,
ask your
sir,
question.
my question is about the components of the encoder and the components of the decoder are quite similar. So, how do they differ from each other and what is the role of each?
Sorry, ma'am, can you repeat, ma'am? I'm just getting a
Yeah,
glimpse of
my
it.
question is we have encoders and decoders in the transformer architecture. So, where I could see the internal components of my encoder, multi-head attention, add and normalization, feed forward. So, the component of encoder and the components of decoder is almost similar, apart from one particular masked multi-head attention, right? So,
Yeah.
why do we have the same architecture in decoder? How does it differs from madam, how does decoder differentiate itself from encoder, and what is the role of each? Why do we have two different things? Why can't we make it as a single thing having all
Yeah.
together?
So basically, this transformer architecture is created for translation. So the encoder will get the English. Let's say if you are doing English to French conversion, English data will go here, French will go here. Now I need to map these components, which means that like both at till this point, it will work very similarly. Only thing is like since this is the output, we just mask it. But basically, multi-attention is the same. If I push this data also inside, so basically for translation, there's only one approach. Encoder and decoder is the only way to do the translation. But for other things, like the generation or any other things, we don't require that because this is the classic way of creating translation. But right now, we can achieve that with the decoder part alone because the decoder part became self-sufficient to do that. But the initial stages, they decided let's keep it separate so that this encoder decoder multi-attention can can able to handle things by mapping this two information. That's how it got started. And that's where they realized, okay, we don't even require these two architectures together, and they just chopped it down into encoder and decoder, and you get some, wonderful lesson with the decoder right now. But yes, there is no, hidden agenda between having, two different tasks. But they decided let's keep it simple by having it separately, so that this weight will be focusing towards in the French translation. This weight will be focusing towards the English translation, English context conversion. Both contexts will be converted and both will be combined here, and then you get some output. So that's the only reason. So there is no other hidden agenda behind it.
Okay, sir. Thank you.
Participants, if you have any queries, can kindly raise your hands. Any of you have any queries as of now, whatever discussed by sir? Okay, sir. Nobody have raised their hand. You can start your.
Yes, ma'am. I'm pretty much done with this session, the first session. So,
Morning. Okay, first session you have completed, huh?
yes, ma'am. Yeah.
Okay, sir. Would you want to have any break of something?
Yeah, maybe 5 minutes would be a little sufficient. So I'll just rest my throat. I'll be back in 5 minutes now. Hope that is fine.